Please pause the video and take a moment to read this important safety message.
Hey, welcome back everybody. Part 5 here in this series, and I thought I'd start out with a few corrections I need to share with you. Some very acute, loyal viewers pointed out a few things to me, and they are absolutely right, and I was in the wrong on this. One of those was the MMFD reading. Remember, we had a 68 MMFD capacitor and a 24 MMFD capacitor in this unit. And I'll be honest with you, I am pretty lazy when it comes to this stuff, so I always use a chart like this, and I kind of scroll down until I find the 68 MMFD like this, and then I will convert it over here and go order what I need based on this. And if you read this little thing here, this is on Just Radios. It says, when reading schematics, diagrams, restoring radios, so on, you must convert between microfarad, nanofarad, and microfarad here. Paper and electrolytic capacitors are usually marked in terms of MF, microfarads, are often written with the little UF symbol. Short forms for microfarad include MFD, MFD, upper and lowercase, UF, MF, and uppercase UF, okay? If that's not enough to confuse you. Then it'll say mica, or in our case here, some paper coupling capacitors, are usually labeled in terms of MMFD, which is microfarads, which I had mentioned. Then they say, in parentheses, picofarad, but short forms for microfarad include MMFD, MMFD lowercase, PF, MMF in lowercase, UUF, and PF. A MMFD is 1/1,000,000th of a MF. It's somewhere in between a microfarad and a nanofarad here, okay? So it says converting back and forth between these things can be confusing with all those decimal points to worry about for sure. And below is a handy conversion chart. Just print it out and tape it to your workbench. I don't have one printed out, but I come to this website quite frequently. And like I said, I just scroll down here till I find the 68 MMFD, and then right here is the common value, which is 0.068 NF. And I corrected that in the video with a little annotation, but I just wanted to come back and walk you through that here so you're aware. Okay, up next in my video, I had pointed out this capacitor here as a 0.02 microfarad, and I said we're going to replace it with, and that's where I messed up. I said a 0.22, should have been a 0.022. Let me show you here. You can see here I had written it down as 0.22. That should change to 0.022 microfarad coupling cap, and we'll need one in each of the amps. So I made that mistake. I'll tell you guys, it is incredibly easy to have one thing in your head and what comes out of your mouth is completely different when you're making these videos. I don't know what it is. I'll be thinking ohms, I'll say volts. I'll be thinking volts, I'll say amps. I'll be thinking 0.22 or 0.022, and I'll say 0.22. I think a lot of it is you're multitasking when you're making these videos. You're focused on the focus of the camera. You're focused on starting and stopping it. You're thinking ahead. You're thinking about what you're going to say next, and not so much what you're saying in the moment. And trying to do all that scripted, just kind of or unscripted. See there? It just happened to me right then. Trying to do all that unscripted plays out sometimes where I say things that aren't exactly as they should be. So just be patient. If you see 0.02 on a capacitor and I happen to say 0.2, don't order a 0.2 if you know the 0.02 is what is right. And please call me out on it. I love feedback. And okay, I'm sitting down on the bench now to actually do the restoration. I'm not going to show that because that's not what this series of videos is about. It's not a video on how to restore a Fisher 20A or A20 amplifier. Remember, this is a troubleshooting series, but I did thought I would just kind of show you. These are the Joe Knows resistor boxes, like I mentioned. You know, I'll sort through here and find the exact resistor I'm wanting to put into the unit. I've decided I'm going to use some orange drop, 0.02 I actually have in stock .02s instead of .022s, which is exactly what's in here now. So I'm going to use some orange drops. I've got some electrolytics for that, and I've got some orange drops for this as well. So I'm going to do that, and I'll just show you the end result, and then we're going to get on to the next video of, showing you about how to troubleshoot problems. That's really what this series is about. All right, I had someone email me this week. I thought I'd explain this while I was doing some soldering. As you can see, I've got a couple orange drops in now. I've got this cathode bypass cap, getting some resistors in here. I got a few more left to go, but this guy sent me a thing and he said, Mark, these resistors these days are just so much smaller than before. If you look, those two are the exact same size 1 watt resistors right here. One's probably a third of the size of the other. Similarly, you can see this here is a 47 microfarad at 50 volts, right? This was a 50 microfarad at 25 volts. No comparison. At least a 10 times difference in size there between these two, and you can kind of see diameter wise. But these are pretty well equivalent. It's just, matter of fact, this one has twice the voltage rating that this one does. It's just technology has advanced a lot over time. The foils and films being used and whatnot have progressed. So don't let the smaller size components scare you. That's what this person said to me, basically. I'm kind of scared to use these smaller components. Will they really hold up like these older ones do? And, we're 60 years into this amp at this point in time, or at least 50. Time will tell, but as of right now, this is what we're working with. Okay, at this point I brought out the second one, like the first one, out of storage, and basically got both of these restored minus one or two pieces at this point. As you can see, I've used some orange drop caps in these. I've put in new resistors throughout, and the reason I did that was really I wanted to make sure all the bias on these tubes was in line. And those carbon comp resistors have drifted up in value some, and they will continue to do so. And so I'm trying to make these units last another 50 or 60 years like they have thus far. So went ahead and replaced those. You can see over here I replaced the safety caps, the depth capacitors as they would call it. Sometimes these old type caps like this would fail short. And these safety caps are designed to fail open. So if they fail short, you can end up lighting your chassis up hot. And in this scenario, they fail open and don't cause that issue. So replace both of those. And then you might be able to see here, I have installed a thermistor. I just came from the wire that normally fed down to the end of the fuse holder. And in line, I put a CL70 thermistor. You could also put in a CL80. They provide kind of two purposes. One, it helps to soften the inrush current a little bit, so it helps with the tube filament life. And two, drops a little bit of voltage here. I'd have to look up the CL70, but it's probably around 0.8 tenths of a volt. And, these units were designed to run back in the day on 110, 115 volts. Now we're pushing 120 volts coming out of our wall outlets. And so every little bit, helps the life of the transformers and whatnot. The only other thing I would call out here is these little capacitors here of this type rarely go bad, but I've ordered some new ones anyway. And the reason I've done that, if you'll notice, this was a 24 picofarad capacitor. Well, over here on this unit, they actually used a 47 picofarad capacitor on this. And if you look in the notes here on the schematic, it'll say, see the parts list for alternative values. And it'll show you in there that some versions of this used one value and other versions they used a different value. But since I'm making these into a pair of stereo units, I want to definitely change this, these to be equal. The same, if you'll notice here, one of these has a 15K feedback, 15K ohm feedback resistor right here. This one has a 22K ohm feedback resistor right here, just like the schematic shows. Well, I'm gonna do a little playing around and figure out how it sounds best, and I'm gonna put in the one that does. But I'm gonna make a match between the two units at that point in time. So all I've got left are these two electrolytics, and I'll replace these as I do that, and then these two, get these two to match up and play around with that on the bench. I'm not going to show you any more in this video because this is really not about a restoration. It's more about troubleshooting. This whole series is. But once I get them running, I will add a little insert to a future video just to show you these units playing, and you know, may put these up on eBay for sale when I get done. So stay tuned, and we'll see about that. All right, I thought I'd leave you with one final thing. For the most part, I have abandoned Facebook these days. The only reason I hang out there anymore is a lot of good forums and groups around hobbies that I'm in. So, you know, this was one around Tube Amp Designers group, and I was able to ask a question. But let me get into the question I asked. So, remember in the amplifier, one of them used a 47 picofarad cap here, and the other one used a 24 picofarad. Well, you know, as I was looking at the schematic, and I came to realize, you know, between the output of this little voltage amp here and feeding into the phase inverter, hanging off the grid of this tube here is this little cap to ground. And that is not something you commonly see. I mean, it is, in my opinion, super rare that you see this right here. And so, you know, I kind of made this post because I was getting inquisitive about this component. And I said, question for the group. The red circle cap, I understand it's a simple low-pass filter of sorts, but not something commonly seen on the grid of a tube in my experience. Curious, how would one go about calculating the roll-off frequency of this filter? What components values would be used in the calculation, and what role would negative feedback play in all this? I get it all conceptually. I just want to understand the math behind the design and how changing this cap's value will affect the bandwidth of the circuit. It's been 30 years since engineering school. I'm usually pretty good with most of these components in an amplifier and what would happen if you raised or lowered this. But this one, I was struggling a little bit because just like the responses I got down below, and I won't scroll and get into the responses and who all responded, but I got a variety of results. Some people were saying, well, this is here to help offset the Miller capacitance within the tube. Keep in mind, when you add two capacitors in parallel, right, that increases. So I'm like, well, that would be increasing the capacitance here. Other people were saying, no, it has nothing to do with this tube at all, and the Miller capacitance related to it. It's more in parallel here with the plate load of this tube. So if you look at this, from this point to ground is in parallel with this point to ground, which would be the plate load of this tube, which would kind of also be in parallel with this resistor here that would, you know, go back through the power supply. So at any rate, you know, basically at the end of the day, you can take the plate load here and this resistor and this and kind of put these in parallel, and it becomes your RC circuit here to give you your filter at the end of the day. But, you know, I was just trying to kind of get to the root, the crux of how to calculate this thing. At any rate, I thought a few people in the forum gave some really interesting answers. You know, Bruce Igniter, he gave me some feedback. He said, Mark, if you think the engineers that designed this amp calculated out the roll-off frequency and picked a value to go in here based upon some real scientific calculation, he said you might be wrong in that assumption. He said more than likely what happened was they designed this amplifier and then they started using it in various scenarios, and maybe one of those scenarios it started oscillating. So this global feedback loop in some way caused oscillation in the circuit. And they inserted this capacitor here to kind of defeat that oscillation that was going on. And they may have just played around with different values until they stopped the oscillation. Another nice gentleman kind of gave me some good feedback. He said, Mark, feed this circuit with a square wave and then look at the output over here and pay attention to whether you're getting overshoot or any critical dampening going on your square wave, and kind of tune this value here to give you, the closest you can get to a kind of a true square wave without a lot of overshoot or critical dampening going on. So I thought there was a lot of good feedback I got in there. I guess the moral to this story is when you post in these groups, you need to read through everybody's comments, and you kind of got to take a little bit from a lot of different things and put together your answer, because you may not have a single person give you the whole complete right answer, and you may have other people give you answers that are not right at all. So anyway, I love these forums for this purpose and love being able to ask others feedback. I mean, there were people replying on this post that work for places like NASA and other places, which probably have a much deeper engineering and design background than I do. I'm much more of a I would call it technician than engineer these days, because it has been 30 years since engineering school for me. All right, we're going to call this one a wraps, and we'll get back to another piece of gear and doing some troubleshooting on it. Thanks for watching, everyone.